This presentation is the fourth installment in a series of videos on the topic of thermodynamic non-idealities in CO2 capture with CAF 20. You can watch parts 1, 2, and 3 on my YouTube channel. In this presentation, I examine the influence of thermodynamic non-idealities on transient breakthroughs of CO2 water mixtures using structured CAF 20 containing 80% MOF and 20% polysulfone. The experimental data that I analyze are published in the paper by Nguyen and Rajendran, published in Industrial Engineering Chemistry Research 2024. The key breakthrough experimental data are presented in figure 9 of their paper that is reproduced here. We have the CO2 mole fraction as a function of the dimensionless time. These are the mole fractions in the gas exiting the fixed bed tube. In this graph, we present the percentage relative humidity as a function of the dimensionless time. And this is the column temperature history as a function of the dimensionless time. The first thing is to note that for a short time period of 0 to 100 dimensionless time units, there is a sharp peak in the temperature, but for the majority of the time interval involved in the breakthrough experiments, more or less isothermal conditions are maintained in the column. On the basis of the experimental data, the component loadings in the adsorb phase can be determined from a component mass balance, and these have been plotted. And the previous presentations have examined in detail why the experimental data on the component loadings do not conform with the ideal adsorbed solution theory for mixture adsorption equilibrium. My objective today is to model these experimental breakthroughs that were determined for 7 sets of conditions for the percentage relative humidity: 13%, 18%, 23%, 32%, 47%, 73%, and 87%. We note that for 73% relative humidity and 87%, 73% relative humidity and 87% relative humidity, the component loadings determined from the breakthrough experiments exceed even the unitary water loadings. This characteristic is not possible to be captured by the RAST, and you can see that the RAST model that is fitted to the experimental data lies significantly below that value. Keep that in mind when we compare the breakthrough simulations using the RAST with the experimental breakthroughs. The analysis of the experimental breakthroughs is discussed in detail in my paper that is available online. The reference is given here. Note that even though the paper is already available online, the publication is dated 1 January 2025. Be that as it may, let's proceed with the analysis of transient breakthroughs. The salient features of the model for performing transient breakthrough simulations are described in this slide. We consider a bed of length L. Z is the distance along the bed, which is packed with adsorbent, say zeolite, activated carbon, or a metal organic framework with a mass m sub ADS. The bed voidage is epsilon. The gaseous mixture enters at a superficial gas velocity of u. Q sub 0 is the volumetric flow rate at the inlet, say in units of liters per second. And the interstitial gas velocity inside the bed is the superficial gas velocity divided by the bed voidage, which is V. In setting up the model for transient breakthroughs, we assume plug flow of gas, assuming negligible axial or radial dispersion. The gas phase concentrations vary with Z and time t, and at any Z t, they adsorbate loadings Qi, say in units of moles per kilogram, within the crystallites vary along the radius. And each crystallite of morph or zeolite is surrounded by a gaseous mixture, and at the surface of the crystallite between the gas mixture is in thermodynamic equilibrium with the adsorbent. The mixture adsorption equilibrium is determined in the simulations using the ideal adsorbed solution theory. The molar concentration Ci of each component in the gaseous mixture at time t in position Z is described by this partial differential equation. The term here, Q bar, is the average loading within the crystal determined by integrating over the volume of the crystal. The adsorber bed is normally divided into 100 slices, and further details of the numerical techniques used to solve the set of partial differential equations are provided in this website. Consider the transient uptake of the gaseous component into the crystallites at position Z in the fixed bed adsorber. The transient uptake of each of the components is described by this partial differential equation, where Q sub I represents the molar loading at the radial position R, and Ni is the flux of component I. The flux of each of these components is related to the gradients of the chemical potential by the Maxwell-Stefan diffusion equations. The Maxwell-Stefan diffusion equations recognize two types of diffusibilities. D sub I represents molecule wall interactions, and D sub ij quantify the correlations in molecular jumps for the ij pair in the adsorbed phase. For solving the set of partial differential equations, we may apply two different discretization strategies. The first one is to divide the crystallite into equidistant radial slices. The second strategy is to divide the spherical crystallite into equivolume slices. The equivolume slices strategy is more efficient because the steeper gradients in the molar loadings occur near the surface of the particle, whereas towards the center of the particle, the gradients in the molar loadings are shallower. In our transient breakthrough simulations, we find that typically using 20 to 100 radial slices is sufficient to obtain good accuracy in the numerical calculations. The input parameters for the transient breakthrough simulations are determined from the details provided in the Nguyen paper. The inside diameter of the tube is 28.2 millimeters. The length of the packed tube section is 78.6 millimeters. The mass of adsorbent in the tube that consists of structured CAF20 is 16.7 grams. The inlet volumetric flow rate is 10 milliliters per minute. The particle density of the CAF20 composite is 570 kilograms per cubic meter. On the basis of this information, the bed voidage required in the transient breakthrough simulation may be determined from this expression. The interstitial gas velocity V is the superficial gas velocity divided by the bed voidage, and this may be determined from information on the volumetric flow rate at the inlet. The experimental data are presented in terms of the dimensionless concentration at the exit, or the percentage or mole fraction of CO2 in the exiting the fixed bed, or the percentage relative humidity of the gas mixture exiting fixed bed as a function of the dimensionless time. The dimensionless time, tau, is the actual time multiplied by the interstitial gas velocity divided by the length of the packed bed. In the transient breakthrough simulation, the intra-particle diffusional influences are considered to be of negligible importance, and this assumption essentially implies that the Maxwell-Stefan diffusivity of each of the components divided by the square of the particle radius is sufficiently large. The transient breakthrough simulations were carried out for two sets of assumptions, one in which the mixture adsorption equilibrium between the gas mixture at any position in the adsorber and the surface of the CAF20 composite is determinable from the real adsorbed solution theory or the ideal adsorbed solution theory, and the objective is to see what difference it makes in the transient breakthrough results. For the 7 different values of percentage relative humidity, the comparison of the transient breakthrough simulation results incorporating either the RAST or the IAST for mixture adsorption equilibrium are shown here. The dashed lines are the simulations in which the IAST is used for determination of mixture adsorption equilibrium. and the colored lines are the ones corresponding to the RAST used for determining the mixture adsorption equilibrium. In all the experiments, the total pressure of the gas mixture is 97 kilopascals, and isothermal conditions are assumed to prevail at 295 Kelvin. I invite you to recall that in the actual experiments, during the initial transient for a very short period of time, there is a sharp temperature rise, whereas for a large proportion of the breakthrough time interval, isothermal conditions are more or less prevalent in the breakthrough experiments. So the assumption of isothermal conditions is not unreasonable, as has been argued also in my paper in separation and purification technology. Let's analyze these breakthrough simulations further by determining the mole fraction of CO2 exiting the fixed bed adsorber and the percentage relative humidity exiting the fixed bed adsorber. The mole fraction of CO2 at the outlet of the fixed bed adsorber is plotted as a function of the dimensionless time, and these are the simulations in which the RAST is used for determination of mixture adsorption equilibrium. This is the percentage relative humidity at the exit of the fixed bed as a function of the dimensionless time. The corresponding results in which the IAST is assumed for these calculations of mole fraction of CO2 at the outlet, a percentage relative humidity at the outlet are shown in the graphs below. You see even a casual visual inspection will reveal that the breakthrough simulation results for RAST are significantly different from those from the IAST. It remains now to compare the breakthrough simulations with the experimental data of Nguyen. The comparisons of the Nguyen experimental data indicated by the symbols and the transient breakthrough simulations incorporating the RAST indicated by the continuous solid lines are shown here for mole fraction of CO2 at the outlet as a function of tau, and percentage RH at the outlet as a function of tau. There are 7 sets of data for 5 data sets corresponding to 13% relative humidity, 18%, 23%, 32%, and 47%. The agreement between the experiments and breakthrough simulations is rather good. The comparisons with the experimental data at the 2 highest values of relative humidity, 73% and 87%, is significantly poorer because the experimental data on the component loadings determined from the experimental breakthroughs show that the water loadings in the adsorb phase exceed those of pure component water. Such behavior is not possible to be captured by currently available theories such as the RAST to describe mixture adsorption equilibrium. Further discussions on this topic is provided in my paper in separation and purification technology. This is the digital object identifier. I invite you to have a read. That was the fourth installment of the series of videos, presentations on thermodynamic non-ideality effects on CO2 capture using Calgary Framework 20.